Hey, welcome to another video of Chem with Com. Today we are continuing gases. This is part two of a three-part series. Today we're going to be doing gas laws. All right. And yeah, let's get started here. I wanted to show you one thing here. Let's hide this first, clean up my screen. Um, it's a pretty cool gas simulation. You could type that long address in, or I recommend just going here and typing in PHET and then gases. You get it here. Um, Hit play. I think it works pretty good on a phone too. I haven't tried it in a while, but let's try ideal gas laws. Um, you could choose between, sorry, it's not coming up here. Yep, what you can do is you could pump some particles in. You could change various parameters like changing the temperature. You could change the volume. Um, yeah, add more particles, increase pressure, things like that. All right, try it out. It might help you understand this chapter. This chapter is not the easiest. I mean, it's not the hardest ever, but want to give you some choices and options to enhance your learning. All right, try it out. Okay, first thing we want to go through is the relationship between pressure and temperature. All right, so on let's say cold water, you have a hot plate is just a device you plug in that heats up, right? Kind of you can cook on it. A lot of lab work you can do on hot plates. Um, we have low pressure. As the temperature increases, right? Hot plate on medium, our pressure will increase. Same with if we heat it up even higher, you get a large temperature gain. And I think a lot of these gas laws are intuitive, like you've seen these things before. And yeah, it's just something you've experienced more in life than the other parts of chemistry where it's kind of like abstract, right? So pressure is proportional to temperature. That's what this sign means, proportional to. So as pressure goes up, temperature goes up, or vice versa. As temperature goes up, pressure goes up. As temperature goes down, pressure goes down, right? And this graph shows it here, right? As we're increasing from, let's say, 0 to 100, we increase from 0 to 20. 100 to 200, we go from, 20 to 40, 300, that puts us somewhere over here, maybe close to 60, right? So as temperature goes up, our pressure goes up. And this is the equation we're going to use for anything that has pressure and temperature. Now, if you recall back to the dilution equation, this one means initial condition. So whatever the condition was at first, 2 means the final condition. And that makes more sense once we start using this. An example, a real life example is your tires, right? They might look exactly the same size, but you should take your tire gauge, take a tire pressure gauge. You can measure the pressure in the tire before you drive it when the tires are cold. Measure it after you drive it when the tires are hot. And what happens is those air particles start moving faster, creating more force, so more pressure. So your tire pressure goes up just by a little bit, right? Nothing crazy, right? But enough to be noticeable on a pressure gauge. One thing I want to point out is that all temperature for gas problems should be converted to Kelvin. So this is Celsius to Kelvin. And you could also go from Kelvin to Celsius using that, but primarily we're going to go from Celsius to Kelvin in this chapter. So this is what's called what was this guy's called? Amundsen's law. Never knew that till now. All right. So again, this is the equation we're going to use. There's going to be four main equations in this chapter. And I'll summarize some of them at the end of the next subtopic. That way we could have just one equation. All right. So again, pressure is proportional to temperature. P1 over T1 equals P2 over T2. All right, let's move on and try this out. So a sample of nitrogen occupies 45 mils at 27 degrees Celsius and 600 torr. What pressure will it have if cooled to 73 degrees while the volume remains constant? So at 45 mils. If nothing changes, we don't use it, right? So because 45 mils is the same before and after, we just ignore that one. All right, let's start labeling these properly. So let's say this is going to be occupies that much volume at this much temperature. So this is going to be our initial temperature, and this is our initial pressure. What pressure will it have if cooled to, and this is our new temperature. This what pressure is going to be our P2 because that's you're asking what it's changing to. Let's write all these down now. P1, T1, P2, T2. Okay, P1 was 600 torr. T1 is 27 degrees C. P2 is what we're looking for. T2 is 73 degrees C. Look here, all temperatures for gas problems should be converted to Kelvin. So let's do that. 273.15, and this is 273.15. This is now going to be in Kelvin. Let's do that math on our calculators now. 27 divided or plus 273.15. 27 plus 273.15, 300.15 Kelvin. We only should have two sig figs here, but we're gonna keep extra sig figs, right? Because we don't want to round too early. We'll round that at the very end. All right, so let's do another one. I believe that was 73. So 73 plus 273.15, and we're going to 346.15. All right, we're almost done. We're actually ready to do the problem now. So now we're going to take this equation and we're going to figure out what we're trying to isolate, what we're trying to solve for. P1 over T1 equals P2 over T2. We're looking for P2. For us to get that by itself, we have to multiply both sides by T2. Look what happens. T2 cancels out, and we're left with exactly what we need. So P2 equals P1 over T1, and we have this T2 up top, so it's T2. We're just going to plug the numbers in now. P1 is 600 torr. Times T2 is 346.15 Kelvin. That's all over T1, which is 300.15 Kelvin. All right, let's check it out. Look what cancels out. Kelvin and Kelvin, we're left with torr. It's asking for pressure, so that's perfect for us. It's going to be torr. All right, let's do the math. All right, so that's going to be, let's clear this, 600. I think it's times 346.15, right? Divided by 300.15. I got 691.95. I'm going to say 692 just for rounding. So let's say 692 torr. Since we have one sig fig here, we have two sig figs here, two sig figs here. We can't have too many sig figs, so it looks like it's going to be 700 Tor, right? All right, let's take a look, make sure that was fine. Hmm. Looks like I might have done something wrong here. Let me just check this real quick. Okay, I figured out what went wrong here. What happened was it says cooled to, but that sign's supposed to be over here, a negative 73. So now we have two different problems, right? This one we're doing, specifically, we're going from 27 degrees, and I did this one to a positive 73 degrees. That's this, and this is the answer for that, right? As your uh, temperature goes up, your pressure is going to go up, which we did, right? So let's try it the way the book wanted us to with that negative sign, right? So let me just redo this part here, and let me just put the negative over here so it's easy to see. Um, so negative 73 degrees Celsius. All right, so let's do that now. Negative 73 degrees Celsius plus 273.15 is going to equal 200.15 Kelvin. Everything else is exactly the same. So let's just fill in the numbers here. So P1 is still going to be 600 torr times now P or T2 is 200.15 Kelvin over 300.15 Kelvin. All right, let's see if we can get that answer to pop up the way it's supposed to. So Kelvin cancels out. We're left with torr, thankfully. You can always do the units. It'll check your work for you. All right, let's do this now. 600 times let's do it on this one. 600 times 200.15 divided by 300.15, and that's going to be 400 Kelvin. Oh, sorry, 400 torr, which was the answer the book had, right? Because I messed up and didn't see that negative there. All right, problem solved. Glad that was his easy fix here. Let me make sure we're still recording. Yep, okay. All right, let's continue. Another one we're going to do is volume is proportional to temperature. All right. And you kind of, I think you can see this. So first of all, let's do the graph, right? As you increase temperature, 0 to 100, right? Our volume goes up. More increase, more increase, more increase, more increase. So volume is proportional to temperature. So as temperature goes up, volume goes up. As temperature goes down, volume goes down. The equation we're going to use is V1 over T1 equals V2 over T2, right? And I think you've seen this. If you blow up like on a really hot day, right? You blow up a pool float to the max, right? Blow it up to the max on a hot day, throw it in a pool. By the next morning, usually it's a little softer because, I mean, a couple of things might happen. Some air might escape, right? But the molecules are slowing down, which gives you less force, which gives you less volume, right? Because the particles aren't pushing as far on that pool float material, right? So again, all temperatures should be converted to Kelvin. So let's try this. Again, volume is proportional to temperature. The equation we're going to use is V1 over T1 equals V2 over T2. Let's try it out. Again, let's see what they give us, right? They're giving us some sort of volume here. I'll call that volume 1. They're giving us a temperature and they're giving us a pressure. Uh-oh, what do we use, right? They're looking for the volume. So they're looking for the V2. They're giving us the T2, but they say same pressure. So we don't have to use the pressure because the pressure never changed. Let's try it. V1, T1, V2, T2. All right, so V1 is 32.2 mils. T1 is 30 degrees C. V2 is what we're trying to find. T2, we can see that negative now, negative 70 degrees Celsius. All right, we have to add 273.15 to each of these. All right, this is going to be 200.15 Kelvin. That is going to be 300.15 Kelvin. Is that the same as last one? 27. Oh, this is 303. My bad. Oh, no, actually, sorry. This is 303. 303.15 Kelvin. All right. Cool. So let's do the equation and solve for what we need to solve for. So V1 over T1 equals V2 over T2. All right. So we're looking for V2. We're going to multiply both sides by T2. T2 cancels out and we get that V2 by itself, which is exactly what we wanted, right? So V2 equals T2 V1 over T1. Let's just plug stuff in. So here we have T2 is 200.15 Kelvin. V1 is 32.2 mils. On the bottom is T1, which is 303.15 Kelvin. Let's do our units first. I always like doing this first. Kelvin cancels out. We're left with milliliters. So let's write milliliters here. And let's do the math now. Let's see here. Looks like we used that one last time. Let's use a fresh one. 200.15 times 32.2 mils divided by 303.15. And we got 21.3. Let's see here. 21.3 mils because we have, oops, this is only one sig fig. This is one sig fig. This is 3 sig fig. So let's just write that down and swap it. So it's going to be 21.3. But because of sig figs, right, we're going to make it 20 mils because we need that one sig fig, right? All right. All right, let me actually just correct myself here for sig figs. And actually, I think I typed this number into the calculator wrong. So let's try that again. But let me do the sig figs for you here, right? So sig fig rules, take a look here. It's 273.15 plus 30, right? So it's going to be 303.15, but addition, subtraction rules, remember, it's the least amount of decimals. This has 0 decimals, so actually the sig fig is over here. So we actually have 3 on each one. So let's actually do the calculator again, because I think I put that number in wrong. So let me just open up the calculator. I think it was the other one we used. Oh no, I had that in there. Okay, so it should be 200.15 times 32.2 minus 70, so 303. Okay, no, I think I did that correctly. Um 200.15 times 32.2 mils divided by 303.15. I feel like I'm doing something wrong, but 303.15. Yeah, that's correct. So it's going to be 21.3 mils, right? All right, because again, the sig fig rules we added, so it's the least amount of decimals. So it should be 200, which is sig fig on the third one, and then 32.3. So they're all 3 sig figs. So our answer should be all in 3 sig figs. All right, let's continue. All right, this is another one similar. So it's another practice problem for us. Check what's the volume of a sample of ethane at 467 K, already there, and 1.1 ATM. If he occupies 405 mils and 298 K and 1.1 ATM. Well, if you look at 1.1 ATM, they're the same. Let's leave them out. Let's label it. So we're looking for volume, and we can call this V1. We can call this T1. This is going to be V2 and T2. You don't have to do any conversions there. So let's just plug it in. V1 equal over T1 equals, and we're looking for V1, V2 over T2. We're looking for V1. Let's move some stuff around. So T1 on both sides. T1 cancels out. So we have V1 equals V2 T1 over T2. Let's just plug this stuff in. V2 is 405 mils. T1 is 467 Kelvin. T2 is 298 Kelvin. Kelvin cancels out. What do we get? Let's see here. Let's clear this. And it becomes 405 times 467 divided by 298. And I got 634.7. 634.7. We have 3 sig figs, 3 sig figs, 3 sig figs. We're going to do 635 milliliters. All right. Cool. So 635 milliliters. All right. Last couple ones, or is this the last one? Now we got 2 more. All right. So next one we're going to do is volume is inversely proportional to pressure, which is called Boyle's law. All right. Boyle's law. And I'm going to try and draw this for you, but let's look at the graph first and looks. So as we get higher, 5, 10, 15, 20, right? As volume goes up, pressure is coming down. So we have an inversely proportional relationship. So pressure is proportional to 1 over volume. So as volume goes down, pressure goes up. As volume goes up, pressure goes down. And it kind of makes sense to me, right? If you have like this cylinder, right? If you make the volume smaller, right? So now it's only this much, the pressure is going to go up. And let's take a look at what's happening here. Let's say we just had, let's say we had 4 particles in a box, right? And it's banging against the sides and the tops and the, left and right, up and down, forward and back. We have some sort of pressure, right? So the volume here is small, and let's say the pressure is high. If you increase that volume size and keep the same amount of particles, those particles are going to collide less with each other and with the size of the boxes. So as the volume increases, the pressure goes down. So it's an inversely proportional relationship, and it's going to be P1 V1 equals P2 V2. All right, let's try it. So this is our question here. The sample of gas has a volume of 30 mils. So this is going to be our V1 at a pressure of 6.5 psi. That's our P1. Determine the volume of the gas. So this is going to be our V2, our question, at a pressure of 11.0 psi. This is our, our P2. But first, let's do A and B. It says, check the sample of gas at the PV graph in figure 8. So what is this? Let's check it out. If we have a V1 of 30, so it's going to be about right here. Or sorry, let's not do a circle. Oops, where am I here? Oh, actually, it's already written for us. So that's great. So yeah, 60 and sorry, 30 and 6.5 psi, which is right here. What is the volume of the gas at a pressure of 11? So pressure would be the second number. So looking for the volume at a certain pressure. Let's look at the volume. Sorry, let's look at the pressures here. This is the pressure. This is the pressure. This is the pressure. This is the pressure. So it's somewhere, if you're looking at 11 psi, somewhere in the middle here-ish. So pressure is going to be 11 psi about here. It's hard to see here, but about right here. So it crosses the line about here. We might say it's maybe about 18 milliliters. All right, let's do another one. 1 over P versus the volume. So what this is they flipped the pressure to make it a straight line. So it's not something you're going to need to know in this class, but it's a mathematical transformation where you can make curved graphs straight. And so let's try this one out. They're saying we have a volume. Let's just mark the first one. So 30 mils and 6.5 psi. So we'll say 30 mils, right? This is our initial one. And so this is going to be our, the PSI at 1 over PSI. It looks like about 0.15. That's not super important. What we want to do here is we want to do 1, and they're looking for volume. So we have to do 1 over 11. So let's check that out. And again, this is not kind of our scope for this class, but I think it's just a fun little exercise. So 1 divided by 11, 0.09. So let's look at 0.09. This is 8, 9, so it's probably here. 0.09. Let's move over here, wherever we hit. will come down, I don't know, maybe about 18 also. So about 18 mils. Using both graphs, it worked, right? This is the one I really want you to know. The other stuff is kind of just for fun. Let's do it. V1, P1, V2, P2. Let's write the numbers down. 30.0 mils. Pressure is 6.5 psi. V2 is what we're looking for. 11.0 psi is what we're trying to, or is what we have for our P2. All right, P1 V1 equals P2 V2. We're trying to isolate V2. Divide both sides by P2. P2 cancels out. Let's check it out. P1 V1, 6.5 psi times 30.0 mils over 11.0 psi. Psi cancel out. We're left with mils. And this is going to be V2. Right, this is V2. So let's do the math. 6.5 times 30 divided by 11. Right? Let's clear this. I think it's 6.5 times 30 divided by 11. All right, so I got 17.7 mils. We have 2 sig figs, 3 and 3, so this is going to be 18 mils, and that's V2. And actually, they're all close. 18, 18, and 18, right? And I'd say they're, we could get fancy and do an equation for these graphs, but the this equation that we used is going to be the most accurate up to this point. Later on, you'll learn that you can actually get pretty cool equations from using the graphs and get really, really accurate results from either way. All right, last one here. Moles of gas is proportional to volume. Avogadro's law. This one I think is the simplest. Just picture a balloon. You have a balloon, it's deflated, so not a lot of moles of gas in there. Blow into the balloon, you're adding moles, so you're adding volume. So again, more moles, more volume, less moles, less volume. So volume is directly proportional to moles. As you increase moles, you increase volume. As you decrease moles, you decrease volume. And so our equation is here. V1 over N1 equals V2 over N2. And don't forget, you can go back and forth to grams on these, right? Because we have the periodic table. So if the question is in grams, you just convert it to moles, right? V1 over N1 equals V2 over N2. All right, let's try it. A 12-liter volume of gas contains 0.000498 moles of oxygen gas. At constant temperature and pressure, so we ignore those because we don't need them. So yeah, we have volume and moles. What volume does 0.0000136 moles of gas fill? All right, let's try it. This is going to be our V1. This is our N1. This is our N2. Let's write those out. V1, N1, V2, N2. All right, this is 12.8 liters. Moles is 0.000498. Then we're looking for V2, and they're saying this is 0 point, and there's 1, 2, 3, 4 zeros, 136 moles. Let's write the equation, V1. And I know at your stage, when I was in undergrad doing chemistry, I didn't like rearranging the equation first. but it really does help and it's easier. It keeps things neater. But let's try it. We're solving for V2. That means we have to multiply both sides by N2. N2 cancels out, so we have V2 equals V1 N2 over N1. Plug it in, 12.8 liters times 0.000498 moles over 0.00013, sorry, I'm missing a zero. 4 zeros, 136 moles. Moles cancel out. And so let's finish this up. I'm going to have to go back and forth quite a bit to get these decimals down. So, or even the first number, I forgot already. 12.8. 0.8 times 0.000498. 498 divided by, now I remember this one's 1, 2, 3, 4 zeros, 136. I don't know how I remember that, but I did. All right, 468.7. 468. That's definitely not right. All right, so let's figure this out. Oops, I switched those. All right. So I switched N2 and N1, so we have to do that over. All right, N1 is on the bottom. 0.000498, and this is 0.0000136. All right, let's do that over. It's 12.8 times 0.0000136 divided by 0.123000498. Okay, a little better now. 0.3496 liters, right? And if you want to do sig figs, which we have to, it's 3, 3, and 3, so it should be 0.350 liters. All right, let's just make sure we did that correctly. All right, looks good. All right, well, that was it for today. Let's call it, and I will see you next time. All right, have a good day, and I'll catch you for the last part of gases.